Well, the Greeks held that the visual arts were the imitation of life, but the computer arts are the imitation of creation itself. Thank you very much.
My name is Frank Kuo. I'm with SRI International, and it's my honor and privilege to introduce Larry Roberts, who was the, I believe, the fourth director of ARPA IPTO, and really the father, although not the inventor of packet switching. Larry Roberts.
The whole issue of workstations is brought up here today, and when we go back into Doug's talk about the early 50s. Of course, I came to MIT right after that, just about where his talk left off in 1958. I started using computers at MIT, and somehow the TX0 had landed in their lap, and I wound up with my own personal computer for 1959. Personal workstation. It was a beautiful system. I mean, it only had 4K of memory, but I had it. I went back in the logs later on, and I found I had used 759 hours of computer time personally on the TX0 during that year, and that was something like 3 hours. The TX2, and both Ivan and I and the other people out at Lincoln had perhaps the most attractive personal workstation that's been around for a long time in that era, because it had the graphics capability that was far exceeding anything that had happened until very recently. One of the things we did back in those days was to do a tremendous amount of display technology and graphics technology until I finally started being concerned is how does this all transfer to the rest of the world? I mean, here we are, we have this beautiful system and we have this fantastic graphics technology and capability of people doing tremendous things on this machine, but we're not moving it anywhere except in research papers published at computer meetings. And it was in 1962 that there was a meeting in Hot Springs, Virginia, that was a military sponsored at the Homestead Resort in Hot Springs. And Licklider and I and Corbato and Fano and Alan Perlis and all a whole bunch of people went down there and talked about the computing industry, of what was going on. And at that point we had, in fact, in my mind, completed time sharing. I remember this is before the world knew about it, but MIT had done it. It was well on its way. Project Mac was, we understood all of the factors involved. And so I was concerned about what was next. After this sharing of our personal computers to multiple people, then what do we do next? And Licklider had been working on this concept of the intergalactic computer network for years, trying to get all of these resources tied together so that we could share resources. And in a beautiful set of discussions, I concluded that really what I ought to work on for the next decade or two, I didn't know it was that long at that point in time, was to undertake to change the communication structure so that we could do this, to do something about linking computers together and building a network. And that was when I decided to do that. It then went into experiments at TX2, between the TX2 and SDC, Q32, two of the machines of that era. We demonstrated that the two time-sharing systems could, on a dial-up telephone line, state-of-the-art at that time, 2.4 kilobits from Western Union, we could establish interconnect between them, and they could run each other's programs and do just fine, calling each other as a subroutine. And either computer could use the other and share resources. We didn't have to have them be compatible because we could run the program on the computer that it was originally written for. That all worked just fine, and we realized at that point that the problem was not so much in the computers. The time-sharing monitors that had been written permitted us to allow computers to be shared just fine. But the problem was in the communication service, and this Western Union circuit was the pits. It really was terribly unreliable, took forever to make a call, and didn't have any throughput when you got going. So we really, and the cost was enormous. So that was the next job, is to undertake how to organize the communications resources. As all of these experiments went on during the mid-60s, at that point, Ivan Sutherland was finishing his tour at ARPA, and Bob Taylor and he were hoping to start some of this network technology, and wanted me to come down to ARPA to help with that program. They didn't convince me of that. So Bob did what he now says I can call blackmailing, and went to the director of ARPA and said, look, you fund 51% of Lincoln Lab. Why don't you call him up and tell him to send Larry down here? Which Charlie Hirschfeld did while Bob was there in the room, and the director of Lincoln called me in that afternoon and said, I think you really ought to go to ARPA. So I wound up down there the next week or two and found myself working with Bob to set up this network program and eventually taking over the whole program. So in some sense, that was how that activity started. It was not quite what I wanted to do at that point in my career, but I found it to be, of course, extremely valuable. Now, during that first year I was at ARPA, which was 67, if I can have the slides, we undertook to develop, with the whole ARPA community and the entire research community, tried to undertake to figure out how to do this, how to build a communications technology which was based on packets rather than channels as we saw it. Rather than set up an end-to-end circuit, we wanted to build something that was based on really the descendancy of the telegraph rather than the telephone. And so this set of slides, which I've reproduced from lantern slides, if you can remember what those were, that we created in -- is the original set of slides we presented that I presented in Gatlinburg, Tennessee in 1967 to describe what we were planning to do. Planning to have essentially a message network, communication network, tying time-shared computers together so that a user at one system could, through his computer system, call through the network to execute programs in other computer systems around the world, around the country at that point in time. Now, you have to realize that nobody was very excited about this except ARPA. The universities said, why do I want to share my computer with anybody else? And no matter how much Luck had talked to them about that, they still had more or less that attitude. And similarly, their data, they didn't want to share that as well. And the communications community basically thought we were all crazy for talking about packets rather than circuits. In fact, I remember during that era of being yelled at and hooed at meetings by DCA and the military communications people because they thought this was sacrilege to start talking about doing communications the wrong way. In any case, we pursued doing this, worked with the ARPA community, of course, thought the communications technology was fine because they were all from the computer field. And Wes Clark, in one of our meetings, came up with the idea of why don't we use what we finally called IMPs to do the communications processing rather than trying to load that all in the mainframes. We had been at that point conceiving of doing whatever we needed to do in the big mainframe computers. These little IMPs that we then created were to be interconnected with either dial or leased lines, and quickly that became, at the Gatlinburg conference, I spent time talking to Donald Davies from the National Physical Laboratory in England, and he convinced me that I was crazy to talk about 9.6 kilobit lines. He would never have the capacity and speed that was necessary, and I should go to at least some higher speed thing. He was talking about 1.5 megabit lines as the right speed channels. We then switched to 56 kilobit leased lines, and after working out the numerics and the message speed and the time through the network, I found that that was correct, that in order to get the throughput we needed, that truly was true. So one of his contributions to this program was to get our speed up to where it was necessary in order to be successful. Meanwhile, Donald had been developing the concept in England, hadn't had the funding to build a network, built a local system in England, and in fact was one of the early sites worrying about the technology and the concepts of it. Much earlier in time than this whole point in time, both of us eventually found out that Paul Barron had done a vast amount of research in 1962 on the concept of what Paul had named not Paul, Donald Davies actually gave it the name packet switching, but what we eventually called packet switching, and had designed for the Air Force essentially a telephone system using packet switching back in 1962. Some of the reports were even classified. Most of them were not in the public domain at all, and therefore neither Donald or I had seen anything of that until we were deep into the design of our respective systems. But that's one of the unfortunate results of doing research in the military and having it pretty well hidden, is that other people just have to redo it. In any case, the original published concepts in the RAND reports were done by Paul, although we weren't able to utilize those in this until later on in this program. The packets we structured at that point were ones which had a header and a content and then a check at the end so that they said where they were going and had error checking. And we even designed a network at this point. This is a hypothetical net. It never got built exactly like this, which I worked out the network technology structure for and the cost effectiveness and the number of hops between all the nodes, and eventually Network Analysis Corporation wound up doing a huge amount of the computation of this kind of thing to optimize this kind of net for us. But at that point, that was the concept of the net. This was in '67, before any net was ever built, and what we thought it might look like, and what we thought it might be organized like in terms of a physical map. So that was the original concept of the ARPANET. And the plan was, as shown here, to have something like an average data rate of 16 kilobits per second and a message delay of 1/10 of a second. And whatever all of that shows, basically down to the average cost at the bottom of something like 16 cents per million bits moved, is something which was pretty well hit in the course of the development of the ARPANET, except for the fact that the volume didn't get up to those levels as indicated for many, many years into the program. I'll show you when. So we started off with this network plan then by going out on RFP and getting Bolt, Beranek, and Newman to build the actual IMP that we finally selected. And we built this first network. By late '69, it was operational, and by '70, it looked something like this. And that network was instantly successful in terms of being effective in both the communications world, in terms of proving that this technology worked, and in the computer world, in terms of linking together these sites. Finally, these computer sites agreed that it potentially was useful to share computers. And in fact, Marvin Minsky finally grudgingly acceded that it was useful to jointly publish documents with McCarthy on the West Coast and be able to share text on the network, after many, many years of saying he didn't want to share his computer. So eventually people agreed to the concept, and it was very successful. That was the network at that point in time. When we went out on bid for this network, one of the things that happened was that we asked the vendor to bid both the hardware and the software. We got back 2 no bids from IBM and CDC, saying to us, this is impossible. The computers you'd have to use are far too expensive and too big. I mean, you must be mistaken. And mini computers were just starting to occur, so that all the other bidders wound up finding that there was some sort of machine that could be used for this. Of course, that situation quickly changed, and everybody wound up having the appropriate machine. Now, that's actually the topology that we used by 1970. And if I quickly show you what the network looked like over time, by that's December 70, April 71, it's growing, and then we made one major change. In August of '71, we added what's called a tip. And you see that on both the East Coast and the West Coast, we have there a thing called a tip. And the tip was the terminal interface processor and permitted users to get on the network directly with their terminals so that they could have direct access to all of the machines rather than having to go through one machine to get anywhere. This was not what we originally contemplated when we built the network. Turned out to be far more important than going through the computers to get at other places, and quickly proved that the right approach is for your workstation to be whatever it is, whether it's from the most inexpensive device on up to the most powerful device, for it to be independently connected to the communication media, not through some other shared environment, which could, of course, fail. And so more and more the users started getting on the network through the tips. And the network continued to evolve in '72 and in August of '72. And at this point in time, in October of '72, and I just skipped that point in time, but in October of '72, we had the big show in Washington at the ICCC, where the network was shown to the International Communications Conference. And for 3 days, everybody was permitted to get on and use all these machines. And that really, more than anything else, demonstrated to the world that this technology did exist and did work. Network kept on growing through '74 and '75, and went on to go to Norsar in England, as you see, in London, and of course over to Hawaii on the other side, and continue to evolve into '76 and 1977. And by this time, there were 400 hosts on the network, and the network had grown into purely a service operation for the Department of Defense. And eventually grew into the Department of Defense network, although its current history is not as familiar to me as it was during that earlier period. The device that we used, that we went out and did, was the IMP, and it was organized, the biggest mini computer available at that time, 12K of memory. And that was a very precious resource. We had to work real hard to get all our stuff done and have enough buffers within 12K. And that probably had more impact on some of the technological issues of how you did packet switching than anything else that went on, because the overall organization was very organized to eliminate the necessity for buffers. Buffers were obviously at a premium with this size memory. We, in the first network designs, had many what you might call bugs, and those were things where you could get a loop, where you could get a deadly embrace between two sites, because one site was holding packets for another site, and the other site was holding buffers for a third site, and couldn't take those packets because there weren't enough buffers. And so simultaneously around a loop such that nobody could move. In this kind of situation, there were a lot of different things which Kleinrock is very carefully listed in some of the works written at UCLA. There were a number of problems that were uncovered, almost all of them to do with the limited memory in these systems. Most of them wouldn't have even been seen if we were using today's computers, because the memory requirements dictated that they were there. In which the first machines looked like this. They were ruggedized machines. We quickly switched after that to the next version, the 316 from Honeywell. This was the 516. And the machines, of course, then evolved later on to whatever was the most cost-effective machine that was being built. Back then, a lot of effort was put into figuring out how effective this was for communications, and this was one of the concept charts that I put out and published during that period of the effective bandwidth of the system versus block size. Much higher effective bandwidth than any other technology that we could find for low block size. In other words, to get a kilobit somewhere, you could move it faster than anything else. But of course, by the time you got up to moving 10 million bits, you could move it probably just as well with a number of different technologies, including dial technology. But if you were going to move short blocks of data, this was by far the fastest. And we also looked at the cost. And the cost, this is the cost of a whole bunch of different technologies, from Telegram at the top at $3,300 per million bits, down to mailing a tape at 3 cents per million bits. And of course, today we have the new option of sending a CD-ROM or a bunch of them by courier anywhere in the world, and having the lowest possible cost that you can imagine for a high-speed delivery. And in fact, the effective bandwidth is over 100 kilobits that way per second. The cost versus delay was a big issue, and the cost per megabit was, as I said earlier, something like in the 16-cent range in a well-loaded network. And if you tried various other technologies, you wound up with all sorts of other things. And the other axis is delay. And of course, the higher delay you have, up to where the delay is for dial-up, the worse off your users are in terms of doing the job. But still, the cost wasn't getting down anywhere near as low. That chart came out of what I've dug up as an even older chart, which was the source of that. Same axes, cost per bit and delay. But on up through tapes on the outside edge, and it's not too easy to read, but those last things going way, way down are mailing tapes and sending tapes by courier and on all of the like. And you see the ARPANET over in the first corner, and all of the leased line networks up above it. And we did a lot of research like that to figure out what the best technology was. Of course, that's all very unique to the time. That changes radically with time. And I'll come back to that issue because there's a lot of things get frozen in people's mind as this was developed, and it's not the right way to do things anymore, what we did then even. The actual traffic on the net grew very rapidly in '73, so that all of a sudden enough people got on the net and the protocols were finished well enough and the software was finished well enough that traffic truly rose to where we had a reasonable loading in terms of network activity. The cost versus network size is something which is the upper line. The lower section in color was projected for commercial networks. Actually, the numbers on that chart typically would indicate that commercial networks charge more than they need to, and they did because they had to do so much more work training the users than we allocated to it in this chart. This is pure cost of communications rather than the cost of running a service. If we can see that well enough, at the top of that chart, it's basically says that the vertical column is the cost per million bits again of moving data. The middle band is between $1 and down to 10 cents for the cost of communications over the years from 1960 to 1980. That chart was one that I published after doing the ARPANET and could, of course, been published even before the ARPANET was done. And what it looked at was a trend analysis. Lick mentioned the computer trend analysis I did very early on, and this used some of that data along with looking at the trend of switch costs that we had seen in the packet switching, and they're both just very similar. And that's that 1.56 per year turned around the way Gordon was talking about it, 36% decrease per year. Very similar to what Gordon found was on his second pass, a factor of 10 every 5 years. And exactly what Lick remembered is the 1.56. That's the computing trend, and that's changed none since the beginning of time. That is, every year I've relooked at that computing cost trend and it has been identical. The cost of delivered computer power goes down by a factor of 10 every 5 years. And that is a very consistent trend, and it includes the cost of the packet switches. The communications trend that I published at this point in time in the 60s, in the late 60s, was one that was coming down nicely. It came down from $1 to 10 cents, as you see there. And so the total cost of packet switching was the combined thing, and you could say, well, okay, by 1980, that was sort of flattened out and was equal to the cost of communications. Actually, what happened to communications is that turned around and started going up again. And you examine communications cost later on, you found that tariff situations, other situations, primarily the FCC and AT&T fighting, caused that trend to go back up again over time. That it didn't stay on the downward side, even though the technology trend for installed plant has continued to go down. Similar to this chart, I've looked at the cost of doing packet switching for voice, and it is a similar trend crossing over in the 1973 time frame as opposed to the 1969 time frame with circuit switching. And what you find is that in this chart, we should have been doing all of our data communication anytime after 1969 using packet switching. And by 1979, most of the world was doing that. If we looked at the voice situation, we'd say that in 1973, we should have switched around and be sending all our voice by packet switching. And by 1993, we may be doing 5% of our voice. It's a much slower process. But at this point, I do believe that the world's telecommunications activities will be moving towards packet switching by voice by the year 2000 for the entire video voice data plant. And that's a major shift, obviously, and it'll take a long time to implement. Okay, now how did all this affect the computing? We built a network. It was very successful in terms of doing data. All of the university groups were involved in that and using it as computer research sites using this network. We forced them somewhat to use the network. We didn't give them any new computers for 5 years and said, use the other ones out there. And so what happened is these sites were built up pretty much as resource centers, having computer power for all the other sites and providing resource capacity through the network. The LAAC-4 at NASA Ames for large computing. The University of Southern California site with PDP-10s in LA, Santa Monica being built up to for a lot of the interactive things, along with many other sites throughout the US. All of those sites provided computer power in about $2 million vicinity per year. All of the sites within the ARPANET then used that for remote usage of about that $2 million a year. But the projected cost, as we then asked them all what it would have cost them if they hadn't had the network and had the ability to share those resources with other people, but had to do it themselves, had to buy their own computer power locally for the job they were doing, and not be able to share it in nighttime hours, off-peak, and or at least buy some machine for their own use, was $6 million a year. So what we wound up seeing was a 3-to-1 cost saving in the computing side of the house. Very time dated. Today, you could buy your computer power for practically the cost of an IBM PC or something, and you wouldn't have this situation at all. Everybody can buy any computer power they want in any modular size they feel like, and you don't save computing dollars by the network per se. It's for all the other reasons that we look at communications, for data sharing, program sharing, and information sharing, as well as pure sending of information, that it becomes tremendously important. But this was one of the goals at that time, and clearly was successful in that respect during that period. Now, out of that grew a number of other activities, one of which was the commercial network Telenet, which is where I went in 1973. And our undertaking was then to make that a commercial activity. And very quickly, and I don't want to spend a lot of time on Telenet since it has much less to do with the personal workstation issue, Telenet was organized in 73. Built the first data network in the world and started operating that, these 7 nodes in the US, and used a device which was similar to the IMP in structure, but as a central office device, so that the user was over a communication line rather than having a device at his site, and or tiled into the site for terminal access. So we had what we call TIPs at all of our central offices, and they connected via remote lines to the user site. And then we might have a small device called a TAC to break it out to individual lines for that computer, or had one X25 or similar protocol line to the user. When Telenet started, there wasn't any X25. We had a similar protocol, and within a year we had changed to the now standard X25. These were the machines we were using. At that time, they were prime computers, somewhat better cost effectiveness than the original Honeywell machines, but similar in concept. The cost that we were able to offer computing power for at that point, I mean, the communications capability was something in the order of $2 an hour for interactive access nationwide from any place to any place. You dial in a network and get to another city for $2 an hour, as opposed to what the dial telephone network charges were at that point of something like $25 an hour. So it was about a factor of 10 cheaper than what you could do it over the telephone network for at that point in time. In the intervening time, packet network charges have gone up to something like $4 to $5 an hour, And the telephone charges have come down somewhat from the $25 range to more like the 15 or 20. So you see a flattening of the two with respect to each other, but the same situation is still true today. We also looked at where packet switching was most effective, and it was obviously most effective for interactive terminals where the average utilization of the terminal on the vertical axis was very low, between 5 and 10%. And the peak transmission rate, relatively low for terminals between 4.8 kilobit down on down. In that range, we could provide very cheap service and have a very cost-effective situation. When you get to very high percentage utilizations, 100% utilization, and very high speeds, of course, you virtually need a dedicated line between the two sites. And the diagonal lines are what it would cost to provide packet switching at the then tariff prices for packet switching for all those services. And you see that batch was quite attractive compared to dial telephone, which is again still $25. And even voice, most of voice, if it compressed at all, was attractive and still is. The next issue that came up, and as remember I mentioned that the people got a lot fixed in their minds in those early days in packet switching. One of the things they got fixed in their minds was the right way to do things was datagrams. A reason for that was that we had lots of communications capacity, basically, because we were using 56 kilobit lines and very few buffers, very little to work with at the computer end. That quickly changed, if you remember the other chart, that the cost of computing continues to go down even after 1973, has gone down by another few orders of magnitude since then. And so now the cost is practically nothing by the time Telenet was built. Of the computing, there's plenty of buffers available. There's no issue about reassembling and doing all sorts of work to set up, to understand the packets at each end of a link. And therefore, the best thing to do is to do all sorts of previous work to figure out what's going on and store it at both ends, in both of the computers at both ends of each link in the network. And so just send a very short piece of header on the packet saying, this is call number 27, and send the data and a sum check. And whereas in the datagram, what we originally did in the ARPANET was we sent to and from and big long addresses which identified everybody and where it was going to and from. That took 31 bytes of overhead, whereas we could get that down to 10 bytes in the upper one. And in fact, when you look at a voice packet switch that we'll be seeing in the late 80s and the 1990s, we're down to maybe 8 bits, 1 byte of overhead on that packet. And everything else is data, because you have to have very short packets. So that we're progressing to very much shorter headers because of the overall capability of the computer side. We can have lots of computer capability to do the best job we can with. And there's no sense wasting that huge amount of overhead when the average data, in fact, was only 30 bytes or 20 bytes in the average call packet. Then we were wasting 50% of our bandwidth and processing power handling all of that data. And so, as it turns out, that was a major change which took place in the packet networks that were done commercially from the research networks. And there were all sorts of claims that it was less reliable or other things, and all those problems had been solved, but nobody who was arguing it has looked at the solutions, so that the issue remains today a debate between the various parties. Telenet also went to a two-level hierarchy where you have a central net, very heavy circuits, and then a lot of finer circuits moving into those. And one of the other things that was looked at was what is the effect of a two-level topology. The top net there is a single-level network like the ARPANET, where every node is equal. Every node has 4 lines connecting to it, and from almost random pattern. The average path length is proportional to the log of the number of nodes. Log base 3, because you have 3 additional lines connecting to each node. a two-level network, which you see in the bottom, where you have a central network and then a bunch of other nodes on the outer, where you have 4 lines per node on the average, but every node doesn't have 4 lines. Some have many more, some have less. The average path length is 3 minus a small amount. And of course, the delay and the cost in the network, because every line you traverse costs you money, the cost is proportional to the average path length. So if you then look at the cost of the network, the path length in the network, which is proportional to cost, the efficiency of the use of the network, you find that the path length in hops for a single level network keeps going up as the log of the number of nodes. And above 100 nodes, it's far cheaper to have a two-level network. And that was what happened in the commercial environment as well. The processors we used at that point were called a TP, and Telenet still uses, by the way, 10 years later. We designed a multiprocessor device that processed the packets and had much higher throughput than the original processors. And as I mentioned, we went into the international standardizations very early in the history of that commercial activity, where every country was 5 countries initially, and then by today, virtually every country in the world wanted to cooperate in providing public data services. So we established what was an X25 data standard in some of the fastest standardization work ever to be known in CCITT. We rushed it through before the other countries knew that it happened to them. And then they all decided that they wanted it after it happened, and at least we had a standard established. And then, in fact, X28 and X29 and a number of other protocol standards were established, including X75, to connect the two networks internationally, so for international interconnection. So all of those standards were created back in the 70s when they needed to be, right at the start of the international data activity, which has had a tremendous impact on permitting this to go worldwide very efficiently. And for the end of these slides, that international network quickly built up then to where Telenet in particular was interconnected with a vast number of countries, as well as TimeNet in the US, and any other network that came along in time. There were a number of commercial networks in the US, and a number of those overseas networks, like UK and Canada, and soon after this France and so on, had their own major networks. Many of them just had nodes. So if we can dispense with the slides, that's some of the historical slides I found to pull together what went on through the course of the network development. And if I can go back to the beginning of all of that, where I was brought up with our own personal workstations, the TX0 and the TX2, and that's what we had at that point in time. It was beautiful. We then developed the network technology throughout this history to where today that's fairly commonplace throughout the country, and of course local area nets within the buildings, such that it is easy to communicate between all of these machines. And simultaneously, computers have been evolving to now where the computers that you can buy for yourself are as powerful as virtually any computer out there. The PCs and the ATs and similar machines on the marketplace are extremely powerful, provide myself, with a personal workstation which is very valuable and powerful, but of course has to be connected to this worldwide network of other systems in order to have the capability of communicating and moving data for electronic mail, for resource sharing of programs, for data sharing, for accessing the combined works of all the other people in the world. So that worldwide network exists, and within most people's buildings, they have some sort of local area network facilities of one sort or another, interconnecting all of their machines with the worldwide network in their own environment. And that personal workstation now can evolve, because we're now at the point where every person can have their own machine, computer, with reasonable computer power. That computer power will just go up from now on. Now, a lot of you have asked me what I'm doing now. And what I am doing at NetExpress, which is a company I founded a few years ago with DHL and Canon in Japan as partial owners, is to work on moving image data, facsimile images, and combining it with text, and building up both the network worldwide and the device, the system, which is basically a combination of the Canon digital copier technology and an AT computer, to be able to handle moving documents in either facsimile form or a combination of facsimile and word processing text form, or in any combination, all over the world efficiently and economically. And what I've seen in that environment in trying to build up the next generation data network is that what we did, what you just saw, was great for when it was, but still needs to evolve another change, because the price that that costs for interactive data capacity worldwide is 10 times what it can be if you're going to move documents efficiently and start really reducing the cost of moving documents to where people will do it, and in fact maybe 100 times what it ought to be. We have been able to reduce the cost of that worldwide packet-switched type service, data service, by a factor of 10 in the deals that we have made with the PTTs throughout the world for this new service, by going to a batch computer service, so that we so that we move data by large blocks in bulk rather than demanding that it be interactive by the millisecond. That's only a predecessor to the major change that will occur, where, in fact, as I said, the whole world will go to a common switch service where voice as the most dominant traffic, and video at the higher end, image traffic that I've just been talking about, which will grow immensely from people moving all their documents and data in that form, so that all of that works over one network. But with respect to the personal workstation, that image issue is, again, very important. And I think over the next year, you'll see a massive change, probably 3 years. I'm always optimistic. And that change, it will be one of where that terminal, much like the terminals at Park many years ago, will have image data on the screen as well as just textual data. Whereas most PCs today are primarily just text. We'll have copies of the documents. We'll have an optical disk, which we see now as being read-write, very high storage capacity, gigabytes of storage on the optical disk, and fitting in the slot in the PC beautifully. That's all happening this year, such that both ROM technology, CD-ROM technology, and CD read-write technology will be available for your personal computer, so that you can have the encyclopedia as well as the Library of Congress at your fingertips. Library of Congress takes a few more disks than just one. But in any case, that kind of capacity is available, and the storage to store images versus just text is obviously there, and you can store maybe not 1 million pages per disk, but 10,000 pages per disk if it's image data. So that the capacity to store and archive your own files and your office files is there with that kind of workstation. And clearly, you still need to connect to the local AirNet and the worldwide nets to move all of this stuff around. But I see the day being fairly close, where I don't have to have piles of paper in my office like I do today. Thank you.
Stick around. Are there any questions?
SIG Troy, University of Pittsburgh. As an ARPANET user in the early 70s, I remember seeing some statistical reports concerning the traffic patterns on the ARPANET. And specifically, as I recall, the usage for electronic mail purposes was significantly high, or maybe surprisingly high. And I just wondered whether you at that time were alarmed by that kind of pattern, or whether maybe some people suggested to you that that was not substantive enough use of such a sophisticated technology, or maybe did you foresee that as just being a significant need to be met in the future person-to-person communication modes?
Well, we were surprised that it happened, not totally, because we had spent, of course, a lot of our time as well developing it. We thought it was fantastic as a capability. And the ARPA office was one of the largest users. The ARPA office converted totally. Steve Lukasik decided, hey, that was a great thing, and he made everybody in ARPA use it. So all these managers of this ballistic missile technology and so on who didn't know what a computer was had to start using electronic mail. I think so. It went over very well inside, and externally, it was probably a larger factor than we had imagined it would be. I remember getting a note back from Paul Barron when we were starting on this. I looked it up the other day when I was going through all this stuff, and it said, this is all fine, what you're talking about for this network, but one thing you ought to watch out is you can't send that personal message stuff. That's illegal, it's against the postal laws, and you'll be in jail in no time. It happened. No, we didn't happen to go to jail.
Alan Newell, two things. The first is sort of a comment. It seems to me that it's worth, we keep looking for the important factors that let these things happen. And it seems to me that relative to the discussion of DARPA, it's worth re-emphasizing something that Larry said, which was that ARPA could remain very cool and easy with respect to the fact that the research community, who it was sort of advertising as its initial main customer, was itself fairly cool on the net. And it had the freedom in some respects to pursue this path for really quite a long time and not necessarily get everyone to get behind it as a set of sort of certified customers before they were able to proceed. And that turned out, in fact, in retrospect, to be exactly the right strategy to make things work. The second one is to come back to, again, an earlier issue. There is a flavor in the meeting so far fairly strong of what you can call technological determinism, which is that if you simply lay out all the physical structure of what happens, then everything sort of falls in line kind of immediately. And the talks, Gordon's talk and Larry's talk to a certain extent, because that's what were on those slides, all really focus on simply not the characteristics of discovery, not the characteristics of who did what when, but just laying out the kind of major economic and technological factors that seem to hedge the whole development in and make it go in particular ways. And it seems to me one wants to keep looking for the factors that worked in the opposite fashion. And one of them, it seems to me, was the issue that got brought up last time. I'm prepared to believe, this is back to the workstation again, I'm prepared to believe that the remarks were right, that it was a community, the research community, which didn't necessarily want to go do the workstation, and Lick said it was the community's fault, and Butler Lamson, I'm prepared to buy Butler's statement, is that they weren't interested in it. Yet, in fact, we did, or ARPA did, a fair number of things where the technology was not available. The network, in fact, is an example of one where you forced the technology by several years, and you hung in there. And the speech was another example where the fact that the technology wasn't really sort of right there and ripe, you took it as your job to kind of force that. And yet somehow DARPA, and so now there's another DARPA guy up there, so he can kind of answer this too. DARPA never took it upon itself to really force that workstation technology as a concept in the long term. I'm not concerned about one or two things like the kludge, because for the network and for several other things that they did it on a scale and for long enough that it actually made the world change. And I wonder if you have some reflections on that, Larry.
I had a lot of reflections as you were going on, and I've been trying to remember them all. The immediate last issue was respect to the support of the personal workstation. Butler's comments, I think, were not the primary issue. That was one thing that went on during a piece of ARPA's history. The primary thing that, from my perspective, at least while I was at ARPA, was inhibiting putting a lot of money into personal workstations, if you will, was that was something that industry could do quite well on its own, and that it was quite within the economic capacity of commercial organizations, and commercial organizations, as you see today, are quite interested in pursuing that. So that was one of the criteria we built up. Don't fund anything that's obviously, going to be done by industry and is straightforward. Fund things that are, more further out. There was another one which Butler was referring to, which is after the ILIAC 4, we said, hey, we've enough of this. Well, we don't have to undertake another supercomputer. But I think, no, I think the thing that stopped the work on the personal workstation was that we had all seen plenty of the research would have led to it. The graphics work and everything else had been done. And the issue was, now it needed to become a commercial reality, and that wasn't ARPA's job, to make it a commercial reality. But, and now I go back to some of your earlier parts here, what you said, and I think that it's very true that the technology is a forcing thing. It brings you there, but as you saw in the network thing, we could have gone for, I think, another 5 years and never had a network if it wasn't for the ARPA office being as free as it was to undertake it. And that's happened with voice. The voice network has not appeared because there hasn't been that kind of undertaking.
Gordon Bell.
Yeah, just a comment that, in fact, we're using the word DARPA very loosely in this, and sometimes it means the collective set of contractors. Sometimes it means a little bit of guidance from the top where let 1,000 flowers bloom. But in fact, in this thing, we really shouldn't be using DARPA. It was a few people, namely Larry, that in fact drove it, and I would say it could have in fact been stopped perhaps because of the DARPA the community getting up in arms of not being funded at their own. They took money out of the communal tree and funded this thing. And I think Larry's being very. I think things could have been much worse. I think it could have been a decade before this happened. I was in this a little bit too, and I've had enough dealings with the communication suppliers, and it's just hard for me to think that it could ever have happened left to its own devices. Namely, it took an individual, it took the experiment to get it to happen. So I think this is one of the cases where the thing wouldn't have happened by itself. I think the workstations all happened almost because of the technology from what was known, but packet switching really wasn't happening, and we saw it, and I wrote this in a little paper, the need for it. Once we built all those mini computers, we had to have DECnet, and so in the 73, 74 time frame, we said we've got to get these things together, and our model was all of the packet switching that was done in the community. We did a little bit differently and used the host to do that. But that was clearly the model, and then I think that was the model for expanding. I think LANs, in fact, there were lots of LAN proposals that were pre-packet switching, loops, Pierce loops, and a lot of work at IBM. But this was truly an individual driving it, and it could have been thwarted both by the technologist, namely the communication supplier, and by the other guys who have gotten screwed by it, the DARPA users.
Doug Ross, just a very brief comment to pick up on Alan's question about why DARPA didn't carry through further with the workstation concept. And I think there are two factors. One is that, well, I guess they're both really the same. The thinking and practice was really focused on the workstation, the WS part, to take the point I was trying to make in my paper, and the software architecture, and much less the user personal work habit question was very hard to get a hold of, especially when the big break took place in going to the PL1 Multics route as the primary time-sharing support of DARPA, and then the still different 940 stuff that was going into what led to the other packet switching and so forth. There was a break in the underlying software technology that had to be reinvented later in the process by the marketplace, if you will. So I think it's really all just one comment there.
Barry Liner. I thought I'd add a little bit of perspective, a little more recent to Larry from ARPA, because in fact, I can remember a number of discussions at ARPA while I was there about the issue of whether we should support workstation work or not. And the position really was what Larry just described, is that it was appropriate for ARPA to support basic research in areas where it could be used to help drive workstation development, but it was inappropriate to go develop workstations because, after all, the commercial world could do that very well, and in fact did, with ARPA encouragement but not support.
Yeah, thank you, because I didn't have the perspective of the last years, but I suspect that that was certainly the case. Certainly when I was there, it would have cost us $100,000 a workstation, and that's a little bit expensive.
David Wood from MITRE. I think one of the major impacts of the DARPA networking on workstations today that hasn't been explicitly mentioned has been the protocol architecture that came out of the DARPA community 10 years or so ago. That many of the networking of workstations has been accomplished using the military standard protocols, and there are some obvious products in the marketplace today that use those, and I think that has to be recognized. And yet one of the maybe not so successful impacts was the selling of those protocols to the international standards community. And now we're faced with a situation where DoD is under pressure to abandon those military standards in favor of international standards, and what the impact of that's going to be on the marketplace and products that have been built up based on those military standards. Do you have any observations on that?
My own observation I gave. I think the military standard is obsolete by this point in time, so that the commercial standard is what most people have built commercial products around, as far as I can see. So I'm not too concerned with that trend. I think it's just correct.
I've got a comment on that one. I actually believe the ISO protocols, the international protocols, were one of the sterling successes of ARPA. ARPA's business is to develop technologies, not standards. And while the standards that ARPA developed may not be used exactly the way they were developed in the military context of the DARPA research, in fact, if you take a look at the ISO protocols, a good many of them are technologically quite similar, maybe updated for newer technology, but still technologically quite similar to the DoD protocols. The question is how to transition inside the DoD, how to transition in some of the other communities that are using the DoD protocols to leapfrog into the ISO protocols, because after all, the ISO protocols are still not exactly a usable set of protocols. There's a lot missing in them yet.
Well, I think we've run out of time, and I'd like to thank Larry again for a most stimulating talk.